Now, the machine learning in general, there are two types. In fact, there are three types, but for us, it is two types only. First is supervised learning. As the name gives you the idea, supervised, that we will take in detail today. And there is another one which is unsupervised. So unsupervised and supervised, we should know exact difference between these two. And the third one is reinforcement learning. So reinforcement learning generally we use when we are like dealing with the like we are developing the games, then we need the reinforcement learning. Then if we are working on a robotic process, then we need to know the reinforcement learning, wherein like from the continuous input stream, we are trying to learn something. Okay, but this is not the case for us. We'll be having a set data which is dumped in the hard disk, and then we have to do some kind of implementation of the machine learning so that it starts recognizing something. Okay, so for us, the machine learning would be for supervised and unsupervised to start with. Now, let's see. If I show you a simple problem statement, how the programmer had thought of, okay, we can build the model just to understand something. So to you can say bring something into as a commercial product or bring something to life, there is a problem statement behind it. So until you have a problem statement, you will not be able to explore any kind of a usage of any specific mathematical concepts or any specific physical concept, or you can say any concept that you learn in the theory, you can't apply it unless you understand the problem statement better. And that's a main task in the machine learning. Also, it's a main task to understand the problem. Until we understand the problem, it's very difficult for us to apply the model, because when I show you the code or when I implement the code, the code in rest of the 80% of the project will remain same. Only 20% tweaking is required. Now, who will do that 20% tweaking? It's the one who understands that problem statement. Then only you'll be able to improvise the accuracy on the basis of the data that you're feeding to your model. So that's for that purpose. The understanding of these concepts is very important. That's why this half an hour is very, very important for you. Now, let's say for an example, there is a bank. Now, we have a bank all over. And nowadays, you see, the bank might have received the credit card or the loan application, more than thousands of applications every day. Now, to deal with those thousands of applications, it's very difficult for them to assess all the application manually. Right? Can you see over here? A credit card company receives thousands of applications for new cards, but each application contains few of the, you can say, credentials. Now, if I talk about 10 years back, what was the scenario? If you are supposed to apply for the loan, or if you're supposed to apply for any kind of a credit card or something, what you have to do, you had to visit the bank, then you had to fill the complete application form, and then after that, they will do the verification, they will do the assessment of your profile manually. There is an employee of the bank who is doing all these assessment and then submitting their complete profile after the verification and everything to the manager, and then manager is deciding whether to approve or not approve that application. And this whole process takes more than 14 to 21 days time. So they say 2 to 3 weeks you will get the decision. Now that's a very long and tedious process. And like 10 years back, that was easy because there were less population, less people who are applying for it. But now in this digital era, there are more than thousands of applications they're receiving every day. So now to deal with those thousands of applications, it's very difficult for anyone to manually assess, because you will be requiring huge amount of workforce to deal with those things. And still nobody can wait for 14 to 21 days to whether to know I should be able to get the credit card or not, or get the loan or not. So nowadays, what is the scenario? You have to just log in on the, you can say, the bank portal. You have to enter your credential and you have to just hit the submit button. More than 90% of the preliminary assessment and eligibility checking, they will do it online. What is happening at the back end? Have you ever thought of what is happening at the back end? So the bank managers have previously, like 10 years back, they realized this problem, that in future it's going to be a very difficult situation for us. So they realizes this problem and they created a problem statement and discussed with the software companies that this is a scenario. Now, what to do with this thing? So the problem is, if you have a physical, you can say, all the information about the client, then what to decide? The problem is to decide whether an application should be approved or not approved. So how we can do that? And I want to do it autonomously so that there is a minimal requirement of manual assessment, so that less number of applications are going to be processed by the manual employee. Otherwise, rest can be automated. So this is the problem which is identified. Okay, now here we are not talking about the machine learning algorithm, but here what we are doing, we are talking about the problem. Now, how to build this? How I can make an automated system which, by just only grabbing the information about the client and trying to give me the result autonomously, that yes, this person should be approved. Why? Because previously you have approved a person with the same similar credentials. This is my manual assessment. From my mind, from my experience, I can tell, okay, this should be the scenario. Previously, you have what the manager was doing. They were assessing in terms of the previous cases. If previously we have approved and that person was never a defaulter and having the similar kind of a credentials, let's approve that person. But it was manual assessment. Now, how to automate that? There is a problem because we don't know how to get this particular task done. Instead, there is no brain involved in it. If there is a brain involved, like a team of, you can say, management who is deciding whether to approve and not approve, that means there are 10 brains who are working on that profile. But now we don't have a brain in computer. That's a problem. So what is our focus? Our focus here, like we should, like how the human learns. The human learns from their past experiences. So because of processing and assessing those past profiles, we can assess whether this particular profile should be approved or not approved. But computer doesn't have that experience. Computer is not like 10 years old experience in that domain, so that they will not get failed. So from where we can learn the computer, like where we can make the computer learn, okay, this is the data, please understand. So computer doesn't have the past experience, but now this is where the most tedious part was getting executed. What the software company developers have done, they have digitized all those applications that were there on the shelf, or you can say store of the bank. Because when somebody is applying for the loan, they have a complete filing, okay, and that file is getting saved in the storeroom after whether they are approved or not approved, just for the record. Now, in that record, what you will understand, in that record, when you take up a file, so over the top, you will see a stamp of approved and not approved. That means we have the information of the client, plus we have the decision also. Now, this is very important, please, everyone. When I have a data with me and when I have a decision also of that data. So decision in technical term is known as labels. So it has so many terms like labels, classes, users, IDs, quality, a lot of names. It totally depends on the data to data what you have, but that is the respective outcome. In a broader term, if I say, so they were having the applicant credentials plus their respective outcomes. Now, this is a gold for them because now they know, okay, by applying some of the pattern recognition algorithm, if we digitize this set of millions of rows with us, we can try to explore something. So they have did the digitization of their data, and they created a data set out of those whole set of, you can say, millions of files. Now, what is the meaning of that? I'll tell you in the next day. So for example, let's say we got the data for the computer in a digital form, in the Excel form or in the database form, but we got the digital data for the computer system to learn. Now, what is our focus? Our focus to learn a target function that can be used to predict the value. Value for what? Value for the whether it should be approved and not approved after understanding the data that we are feeding in. So this type of a problem statement is known as supervised learning, where you have a data set with you In the data set, you have the attributes. Attribute is a technical term for the features. Means in this case, the credentials of the client. The credentials of the client will be treated as an attribute, and their respective outcome is treated as the label. So when you have a data attributes and the label associated with it, okay, all together, then this becomes a supervised learning problem statement. Okay, so once you have the data and its respective label, then now you should know that this is a supervised learning problem statement. Then we seek for any kind of a supervised learning algorithm to be applied on this data. But there are certain rules, like where one algorithm will do good and another algorithm will not do good. So we need to understand those problem statements also. But here, this is a broader term, supervised learning, that can be applied on the data sets which is having the data along with its labels. This is something to remember. So this is what, when we say data, that means we have attributes like multiple features, like different column headers in the Excel file. I'll show it to you in the next slide. And class is what? The label, the predefined classes. In our case, in the credit card application, the class is approved or not approved, high or low, 0 or 1, right? So now the goal is to learn a classification model. So earlier I used the target function. Now it becomes a classification model, because now we got to know that it's a supervised learning algorithm. And the first application of the supervised algorithm is classification, build the classification models. In another term, we say recognition models. Okay, so that's why to learn a classification model from that data that can be used to predict. This is our data attribute. So whenever you see any Excel file, just to start with, we generally process the Excel file to start with, then we move towards the databases file. So whenever you see the table in front of you and you see the column headers, just try to read those column headers. So in you by yourself will understand, okay, this is a set of information. It could be anything, but these are the set of information, and then might be having some class associated with it, means the respective outcome. So when you say respective outcome, so this is my label, class. Then can you see the decision? No, no, yes, yes, no. So if you have, let's say, age is young, has job, own house, credit rating fair, then no. Then you have few yes and then few no. So this is what the digitized form of that data which I was talking about. So can you see that? Let's say this is only 15 samples. You might have 10 million samples. Now to build the model for those 10 million samples, you need a very huge infrastructure, digital infrastructure, because it will take, you can say 10 to 15 days of time just to train. So this is where like we need to understand what kind of infrastructure is required to process what kind of data. Because at that point of time, we were not having a concept of these big data concepts that was evolving. Now, so now we have a data ready with us. What to do with this data? So now my task is to learn a classification model from this data. For what? For classifying the future loan application. Why I'm doing this thing? I'm doing this thing just to start predicting my future loan application, so that I should not have those huge team of people just to do the same thing. This is a repeated task. Okay, so manually assessment should be removed and everything should be done autonomously. So that's my requirement. Okay, so now for that purpose, we have prepared our data. Now let's try to understand the classification here. So if you see, now we have to learn a classification model. Because now I'll be requiring the slideshow. Yes. Yes. Now see this. So now we need to learn a classification model here from this data to assess the future applications. Now, for an instance, let's say this was my training data, the data which I digitized, which has the class associated with it. Now I'm going now to just see how my test data will look like, or the future loan application will look like. The client who is actually landing, clicking on my landing page and filling their information, they're actually giving me these information, right? So what they don't give me? This. So what my classification model should predict? the classification model should predict this. So what we do, we have this new data which was not there for the training purpose. While I was making my classification model learn something from that data, this particular case was not there. This is a runtime data which somebody else who is a live client is actually feeding that data in my system. And now I will be training, or like I will be passing this data to my trained model, so that this trained model, after assessing this, will give me this prediction. So this prediction I will process. See, the machine learning algorithm only give the result in terms of either digits, either categorical like 1, 2, 3, 4, or let's say high, low, right? But you as a programmer or application developer, you have to use that value to give a legitimate response, because nobody will understand if the user will get 0, he will not be able to understand what is the meaning of the 0. So you have to prepare, like if the result is 0, then you have to prepare a proper response, like proper output. Okay, you are not still eligible for it. You just have to wait for some more time. Your credit history is not that good. So at least a response you as an application developer have to write it. Machine learning algorithm only will give you the output in terms of digits. And those digits explanation, you should be ready with you. That should be ready with you. That's very important. Okay, so I hope you understand this part. So what is the meaning of future loan application? So in our technical term, we say these are the test cases. So test cases will only have the data, not the label. So label needs to be predicted from the classification model. That's the basic of it. Okay, so this is how the complete example was executed. First, we understood the problem statement. Then we tried to digitize the data. And then we try to understand that, yes, it's a classification model. Then we understand the data. Then we learned our classification model from that data and its respective labels. And then we predicted a future loan application. So in these 5, 6, 7 slides, what you have understood that this is how the machine learning model problem statement understood, built, and got the result. So it's like that. So this is 2-step model. One is training, one is testing. Let's say, for example, I have 10 million of a data with me, okay, which is having the data set plus its respective labels. I have both the things with me. So what I'll do, I have to train my classification model. So that doesn't mean I'll be training it right away on the 10 millions, and I will not be assessing the performance of my model. And then directly I'll feed it on my server so that it can start taking up the new values. I will not be doing that. Why? Because we need to first understand whatever model which is being trained, is it good model or not? Is it giving us sufficient accuracy or not? If it is not giving us sufficient accuracy, then we have to retrain it. Then again, we have to retrain it. But how we will compare? Because we never, we never test the model with the same data for which we have done the training. So that is where you need to understand little bit thing over here. So now let me show you. For an instance, I have over here, let's say 10 million data set. Okay, I have a 10 million data set with me. Then now what I do, the first task which I do is I will divide the data in 2 parts. Let's say 7 million tests trained and 3 million tests. So can you see what is this percentage? This percentage is 70:30. There are certain benchmark train and test ratios like 70:30, 80:20, and 60:40. So these are few benchmark train and test ratios. So we try to do it in that way. So can you see that now I have divided this data. So earlier I was having this data with me. Now I have divided this data into 2 parts. One is your training data set and one is your testing data set. Okay. Now what I'll do, I will take the training data. So this train data is going to get passed in training algorithm that we term as a classification model. Okay, so I'll use this term classification model. So what I'm doing over here is I'm passing only this 7 million to this trained data classification model. That's what is being shown over here. This is my training data, and now this is being passed to the training algorithm or the classification model. What happens over here is, for us, like, we should understand only that the training is happening until we go deep into that, how the training happens. But for you right now to understand is the training will training will happen. What is the meaning of this training? This classification model will try to adjust its hyperparameters in such a way that it will start understanding, okay, these 10 type of a data belongs to class 1, and these next 10 data set belongs to class 0, and so on till 7 million completion. So it will just understand, okay, this pattern data belongs to one class, other type of a pattern data belongs to other class. So once we do this training, then we say that we achieve not the model, we achieve trained model. Okay, so what we achieve? We achieve trained model. So this is the part of my training data set. So when we pass this data, what we are passing? This we have to understand. We are passing this arrow, we are passing the data and label both. Here we are passing what? That's very important. Data and labels both to the training algorithm. And then we achieved what? The outcome of the training is we achieved the trained model. Now, what to do with this trained model? Then what we'll do, let me change the color of it. Then we take this test data and directly come over here. Now, what we are passing in it? Please, we are passing only the test data, not labels. We have the label of the test data, but what we are doing, because since it's a trained model, we are only passing the test data to it. Please understand, not the labels. Why not the labels? Because this test model, when this model is going to get process this test data, what it will produce? I'll write it over here. It will produce predicted labels. Okay, and actual test labels we already have with us. Got it? Now this is where we need to assess the performance of the model. How? Can you see this definition of accuracy? Number of correct classification divided by total number of test cases. So for us, total number of test cases was 3 million. Okay, those 3 millions actual data set, actual label I was already having with me. But what I did, I only passed the data to this trained model, and then we try to compare. Okay, out of 3 millions, how many data set were correctly classified, like it was a class 0 and really predicted as a class 0. It was a class 1, really predicted as a class 1. Okay, and that makes your accuracy. So if we are getting accuracy above 85%, then we can say, yes, our model is good enough. Okay, so then we can think of move towards the finalization and put it into the production. So this is where, before putting it into the live data set, we have to assess the performance of the model within our current data, no matter how short data you have. If you only have 100 samples, you still have to divide it into training and testing. But we have another set of implementation that is known as cross-validation. But right now, you're not at the stage to understand the cross-validation. So forget that. But here, you just understand in this simple term that there is a data set. Then we have to divide that data into two parts, train data set and test data set. And once we do this division, for the training data set, we do the training part, means and making the algorithm understand, making the classification model understand that this type of a data belongs to which class. And then once you complete the training, you achieve the trained model. Then what you have to do, you have to assess the performance of that trained model. How you can do that? For that purpose, you have to pass only the test data, not its respective labels. You save the labels with you. So you are just passing the test data to the model, trained model. Then you will achieve some predicted labels equal to the number of samples. If you are passing 100 samples as a test data, you will receive predicted test 100 values. And then what you'll do, you do the comparison. Okay. So you do the comparison. That means how many are correct, how many are incorrect. Now, at each stage, you have a lot of algorithm to work. So that purpose is being solved very nicely in Python. You're not supposed to write any function anywhere. You have all those pre-built function in the library that is known as scikit-learn or sklearn in a shorter form. So sklearn is a library which have all these functions. If you're looking for a classification model, we have 7 to 8 classification models. If you're looking for accuracy, so we have more functions related to accuracy, precisions, recall, F1 score. So we have all those functions with us. If you want to split the data autonomously, we can split the data using one function. So you don't have to write manually anything. You just need to write everything sequentially and you will see the model building. You get the model nicely. But are you able to understand that part or not? So this sequence is very much required to understand. So what do we mean by learning actually? We have a data set, we prepared it, we have a task, means the function to be learned, and then we have to measure the performance. Now, how to improvise means how to learn. So what we do, a computer system is set to learn from the data D to perform the task T if after learning the system performance on T improves as measured by M. Can you see that? It's very complicated sentence, right? So just in simple term, we are trying the data by just having the classification model, and internally it is calculating the performance autonomously and trying to retrain it until and unless it reaches to the maximum performance. Then only it says that yes, we have received the trained model. It's like that. So when it says trained model, that means internally it has done the iterations thousands of times just to reduce the loss. Loss means this particular class data belongs to class 1, and until you get the class 1, the loss will not be 0. So it tries to remove, you can say, improve the accuracy in terms of doing the retraining again and again. Okay. Now, when you just simply create a classification model and try to pass the test data to it, it will give you very bad accuracy because that's an untrained model. So until unless you train your classification model, it is useless. So that also we need to understand the untrained model and the trained ones. Okay, so we'll do it on later stages, but forget this. The most important part is this one: assumptions. Assumptions with the help of which, like when we get the higher accuracy, when we get the lower accuracy by just looking at the data, by assessing the data preliminarily, we can tell. Why? Can you see this? Now we have divided the data into two parts, the training and the testing. So if the training and testing data is almost identical, so in theoretical, we say if it is completely identical, then you will tend to receive utmost highest accuracy. Then your algorithm might not do any mistake because you don't have any noise in it. The actual and the testing and the training data both are almost similar. In scenarios, you will have real-time constraints, you will have real-time data. So always this might give you or tendency to give you some errors. So now in practice, these assumptions which we are thinking of is often violated. Now, if it is violating to a certain degree, like 10 to 15%, no problem. Still you get the good enough accuracy. But the strong violation of these things, like your test data and training data, is totally different. If they are totally different, then it results in a poor accuracy. And that's a problem. Okay, so that's why we say to do the training, we should make sure that we are passing a sufficient data to my trained model so that in turn you will get a good enough testing accuracy. And it will process the new unseen data in a more better way. So this is the assumptions we need to understand. Okay. For an example, if I talk about the face recognition system, that's where you can see this assumption get often violated. Or on your mobile phone nowadays, that's a real example that you might face every day. You have the fingerprint sensor. Almost everyone is having a fingerprint sensor on their mobile nowadays. Now, when you put a thumb, so what we did, like when you purchase the phone, So first time you just open it using your thumb? No. So first you enroll your thumb for the authentication. So that enrollment is the process of learning. That's what you're passing. You're passing a trained data of your thumb to your classification model, which is there inside your phone. And it is learning that, okay, this is the features of the fingers which I have to learn, because next time I have to unlock the phone for that respective data. So it's just you're feeding. So it always asks you, please put your thumb in a different angles, move like that, move like that. Why? Because it's asking all the different possible data set of your thumb or any finger, so that you put your thumb in any which way, I should be able to recognize it. So that's a sheer real example of classification model that you use every day, but I think we don't know it. So that's first simple example. Now you just color your thumb and try to recognize. You might not be able to. You just have a cut on your thumb, then try to recognize. It might not be able to recognize it. So that's where you have the problems. Violation. There is a cut in thumb, so feature got distracted, completely different. Okay, so little means if you have a little bit of dryness or little bit of dust, then still it can recognize you. But if you have a complete coloring of the thumb, it might not recognize you. If you just you can say have a wet thumb, so your feature got completely deteriorated, so it will not recognize you. So this is what you need to understand. What is the meaning of the strong violation of the data sets, or while we are passing the data set in real time? So this strong violation is often there. That's why it doesn't recognize you in some different circumstances. So that's your fundamentals of assumptions. Now there is a last part of it. Now, so accuracy, I think we have already seen it. Accuracy is number of correct classification divided by total number. This case is pretty simple. But there are certain other, these are what qualitative measures. Please understand. If we are applying two algorithms on my same data and they're giving same accuracy, then how will I differentiate between those? So for that, we have some quality, like we will assess the efficiency of the model. How we assess the efficiency of the model? How much time it is taking to train the system. Let's say one model is taking 10 days of time to train 7 million data. Another model is taking time to train the data and giving same accuracy. So which one is more efficient? The first one, which is taking 10 days. So that's one thing. Then when we are passing a test sample to it, time it is taking to give me the predicted result. Let's say one is giving you result in 1 second, one is giving you result in 3 seconds. So that's like 3 times slower. So that's where you have to understand that that's the efficiency measure. How much time it is taking to train, how much time it is taking to give you the result. Then second, how much robust your system is. Robust means how much better it is handling the noises. For example, if you have certain violation wherein like you have added up the noise in your data, but still is it able to recognize you or not? So most of the algorithm get failed when you have a huge noises. And are we able to handle, the algorithm itself is able to handle the missing values in the data set? Because when you have millions of data sets, it's next to impossible to give you a complete clean data. So you might have a missing values also in that. So are we able to handle those autonomously? When we are able to do that, then we can say our model is quite robust. It will handle all the things autonomously. Then scalability. That's where we talk about. Currently, we are only processing 1,000 to you can say 5,000 samples every day. Now, when you have the portal up and live, and now it is being popular among the users, and now you have 10,000 of it every day. So are your model is able to handle those 10,000 of hits every day? So is it that much efficient, or do we have a concept wherein we are scaling our model? So that's the scalability. The next point is interpretability. Interpretability is very important, which we don't find in all the models. Interpretability means like, are we able to understand how my model is giving the results? Be able to understand if I'm passing 7 million of data to it, how it does the training of its parameters so that it is able to recognize this data belongs to that class, this data belongs to this class. Yes or no? If we are saying yes, then it is highly interpretable. If we say no, that means we don't know what is happening. So it's not at all interpretable. So random forest is not at all interpretable. And decision tree gives you the result in a nice flow chart. So we understand everything by looking at the flow chart. So that's where we say the interpretability of the model. Compactness is something which is very crucial. It is at the last, but it is very crucial. If your model is taking GBs of the space, then these biometric devices that you have now, or in life you have the model, build model, have the capacity to not be having those systems. And that's the reason nowadays we have a compact trained model which can be stored in MBs of the data. So it doesn't require much of a memory. And that's why nowadays we have a very cheaper cost biometric devices which have the capability to contain 200 users, 2000 users in a little memory space, because memory means costing. So that's why we were not having the commercial product before 5 to 6 years related to machine learning, even though the algorithm exists. But nowadays, due to the compactness of these models, we have a commercial product which have the machine learning capabilities embedded in them. So we have embedded devices, electronic devices, which are having these machine learning concepts. So it's like this. That's compactness. So these are all what? Qualitative measures of the machine learning applications. But there are certain quantitative measures as well. Quantitative measures that we measure using certain values. So we have to calculate those values. Even though we are not supposed to manually calculate those, but we need to have a good understanding how it is being calculated. Okay, so that we should not be blank when someone asks me this thing. And why am I spending time in explanation of these things? Because until unless this basics is clear, nobody will ask you the advanced questions. No one. So first they will assess you whether you have understanding or you just downloaded the code and build the models. Anyone can build the model by downloading it from the internet. In GitHub, on Kaggle, you have thousands of code available on thousands of different data sets. But are we have a good understanding of it or just hitting the run button? So there are two things, right? So we need to differentiate in between those two. So if you see over here, these are very important parameters, evaluating parameters. And I'm really shocked to see that these precision and recall, I found it in the 10th standard AI book. And I was really shocked at that time because we understood these things, these concepts when I was doing a research project like after my college, not inside the college also, I didn't knew about these concepts. So nowadays it's available to the, and that is must for the 10th standard kid, no matter if it is going to have a science or not, but this precision recall, accuracy, F1 score, machine learning, they should know about it. So that is really very good. Now, this is precision and recall measure. To calculate these two things, we have a confusion matrix. And I'm sure, and I promise you that actually this is a confused matrix. And if you understand this confusion matrix, I'm telling you, all the evaluating parameters will become a very easy for you, very easy. But as the name gives you the idea, so it's really confusing. Okay, let's understand this part. And to calculate the precision and recall from the confusion matrix, you need to understand these four terms. Okay, in English both, just to make you a good enough understanding of what is TP, what is FN, what is FP, what is TN. So when I say TP, that means total number of correct classification of positive examples. Very nice explanation, right? But what is it? I don't know. So true positive. The full form is true positive, false negative, false positive, true negative. Let's try to build this. So I'm just minimizing it and opening up the Excel file. Please let me explain you with the Excel file over here. Just imagine that you have credit card applications. How many? Test applications. Let's say approved. Approved. How many approved? Let's say 12. Not approved. Let's say 12. Okay. So I have 12 approved and 12 not approved. Credit card. Now, please. Let's say approved not approved, again approved, not approved. Now, so this is what this is actually actual. Okay, and this is what, please try and understand, predicted. And now let me write this here, please. If you see, how many total approved were there? 12. How many total not approved were there? 12. Now let's say out of 12, actually this was approved and it was predicted as approved. Like that, we have to understand this. So it was 11. And then out of this approved, one is misclassified as not approved, predicted as not approved rather. So can you see this? So if you see here, out of those 12 in predicted, approved is only 11 out of 12 and not approved is misclassified. So if I sum it up like this, it should be 12 because actually the approved sample total are 12 only. But out of those 12, 11 is correctly classified and one is misclassified. Let's talk about not approved now. When I say not approved, then this is not approved and not approved matching. Let's say 10. And not approved 2 are being said as approved. And that's a major problem. But we'll talk about that problem later on. But this is how we build a matrix, wherein on the left side, the row is having the actual data and the columns are having the predicted data. And these are the diagonal terms. So diagonal terms always define this. Let's say these are the diagonal terms. The diagonal terms always define your correctness. So first thing, from this confusion matrix, this is known as confusion matrix. And this confusion matrix will become so complex when you have a larger category of the data. Currently, it is only 0, 1. But let's say if you have 40 user data, 100 user data, then it will become 100 by 100 matrix. Now, to evaluate from that, it will become very difficult. So that's why we use the function. But we need to at least have a good understanding of how we are getting it calculated. So please understand over here. When I say true positive, so true positive and false positive, everything gets calculated class-wise. So let's say true positive for approved. True positive for approved. It always gets calculated class-wise. We need to remember that. So true positive approved. So true positive means in a simple term is truly positive. That means it was a positive sample and predicted as positive. Just understand in that way. वो पॉजिटिव था और वो डिटेक्ट भी पॉजिटिव हुआ. सो अप्रूव्ड कितने सही हैं? Approved are correctly classified as 11, right? So we say TP of approved is 11. First thing. Then FN of approved. The next term. The number of incorrect classification of positive example means falsely negative. It was not negative, but falsely predicted as negative. So I can just simply write in a term, falsely negative. वो negative नहीं था, but उसको negative मेरे algorithm ने समझ लिया. It was a positive example, but incorrectly or misclassified as negative. कितने हैं इनसे?
2, I guess.
Approved is this. This is correct. And when I say this one, so this was a positive example, but predicted as negative.
1.
Yeah. Now, the most dangerous thing. FP. FP means false positive. Was not predicted positive. The positive negative sample positive detect हो गया. So predicted as positive, but it was actually a negative. So we can say falsely positive. गलती से positive. positive. How many? Positive or predicted positive is this. Correctly is 11. Incorrectly 2, which is negative, but actually detected as positive. This is so that's your 2. Falsely positive. It was a negative sample, but predicted as positive. So you have to check over here and then leave the diagonal element, and rest all are your false positive. So 2. Then one more. Truly negative.
10.
Yes. It was a negative sample and correctly predicted as negative, that is 10. So that's my first thing for approved. Now, same thing needs to be repeated for not approved. Now, here if you see NAP, 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 NAP. Can you tell me now this? For not approved, all the approved are -1. Okay, because now we are talking only about not approved. So all the samples of approved will become negative for it. So can you tell me TP for not approved? So with 2 classes, it becomes so easy to understand. For multi-classes, it becomes a little bit difficult. But this is what we have calculated. We only have calculated the TP, TN, FP, FN. Okay. Now, with the help of these parameters, we calculate very important stuff, that is precision. So the formula of precision is, if you see it in the next slide, the formula of precision is TP upon TP plus FP. It has nothing to do with how many samples you provided. It is the number of correctly classified positive examples divided by total number of examples that are classified as positive. That means we are talking about the system here. For example, if we say approved, so how many are actually correctly classified out of the total number of samples classified as approved? Which has nothing to do with how many samples I passed for it, but how many are classified as approved, and out of that, how many are correctly classified. So that is why it is, if you see the presentation, that's why it is TP upon TP plus FP. Because FP is galti se positive, falsely positive. So when I write this, TP upon TP plus FP, like this. That's the formula. Let's calculate that. TP upon, round bracket, TP plus FP. Okay. Yeah, now it's fine. That's what I was wondering. Can you see that this is 84.65? Okay. Now let's call the recall. Recall is class-wise accuracy. How many samples you passed and how many are correctly classified. That means we check it like that. 12 upon 11. So this is TP upon TP plus FN. That is nothing. It's just how many samples you passed and how many are correctly classified. So that's class-wise accuracy. So that will become over here 11 divided by 11 plus false negative. 91.6. Okay. So that's your precision and recall. But what to extract from it? What to understand from it? That's very important. When I say precision, see, it's very next to impossible to achieve 100% accuracy. Next to impossible. What is the meaning of 100% accuracy? If I'm passing my, let's say I'm sitting in front of a camera and there is a face recognition model is running at the back end. And when I'm passing my 20 samples, 20 times I'm in front of it, and out of 20 times, it has detected me 20 times correctly. It's next to impossible. Because it will give you some false, let's say, false classification, false recognition. That's what I'm saying. I'm passing 100 samples, and out of 100 samples, it is detecting me correctly 97 times. No problem. I'm okay with it. But it should not match me with anyone. Let's say, for example, I have a security-based system, and that is recognized by fingerprint. So my fingerprint, who is authorized, should not match with any of the other person. If it is matching, that means there is a false positive. That person was not authorized, but due to his, you can say, finger matching, that match with any of the authorized person, and the gate is open. So this is very crucial point to understand when we talk about the security based systems. When you have a secure system and only authorized person can enter over there, so the false positive should be zero. So when you make false positive zero, see, this is false positive. What is the effect? You see the effect, please. If you make the false positive zero, autonomously your precision become 100%. And precision we want 100%. So why we have these parameter? Because practically achieving 100% accuracy is next to impossible. If I'm putting my finger 100 times, I will get recognized 100 times, not possible. But if I'm pressing it 100 times, out of 100 times, it is recognizing me 90 times correct, and 10 times it is saying, please place your finger in a proper way. Please place your finger in a proper way. No problem. I'm okay with it. But it should not match with any of the third person. That's what I'm trying to make you understand. It should not match with any of the other person. It will always say, not found, not recognized. Please stand in front of the camera nicely. Please put your face in the square box. No problem. Otherwise, you are in your office and you are doing the biometric entry. You are just making your face in front of it, and the person who is absent is getting logged in. Why? Because your face is quite matched with that person's face, and then it got recognized. That is the meaning of false positive. But nowadays, that never happens, because what we do as a developer, we focus more on zero false positive. And that's why these parameter comes very crucial when we are building a model for real applications. So false positive has to be zero. So you see the effect here. As soon as I make the false positive zero, I got 100% precision. And as you increase it, the accuracy decreases. Now see, the recall, the class-wise accuracy is 91.6%, but due to this two false positive, we got the precision 84.6. So precision is degraded. And that's why these parameters become so crucial. So everyone will ask you, what is your precision of the model? And you see in your biometric, you see at the back, they will show you the error rate. What is the error rate? What's the false positive rate? If it is more technical, otherwise they'll show you the 100% precision like that. So they have noted down everything over there. What is the error rate of the system? So this is what I was talking about. And that's why these parameter understanding is very important. Now, one more. Now, the researcher, the mathematician have no work. They have to just do the research every year. So now we have the accuracy with us. Now we have the precision with us. Now we have the recall with us. They give us one more. What is that? I'll tell you. That is F1 score. So they're just playing with the numbers. Can you see that? F1 score is nothing. It is being built using the precision and recall. So F1 score is 2 PR upon P plus R. Okay. So now let's say if you have higher precision and higher recall, then automatically you get higher F1 score. So what is F1 score? It's a harmonic mean of 2 PR upon P plus R. So how we calculate this? 2 into P into R divided by P plus R. So to have the F1 score higher, your precision and recall both should be higher. For example, if I make it 0 here, so you see this, it becomes 95% because your precision and recall both are at the higher end. Okay, so now I'll just copy this so that class-wise I can calculate it for this also. See, it will be auto-calculated formula. Okay, so now this is what I was supposed to tell you in terms of evaluating parameters. So these are all quantitative parameters wherein we have the numbers. Okay, so this is a little bit explanation of it just to make you understand what is precision, what is recall, what is F1 score. Now you want to calculate the accuracy of the system. That also can be done using confusion matrix. How? Sum of the diagonal elements divided by total number of elements. Now let me say accuracy of the system, the complete system is this plus this divided by sum of all this. Wow, what accuracy it is. Okay, this should be in bracket. Can you see that? 87.5%. So that's my accuracy. That's a system accuracy altogether. I'm not talking about the positive and negative. That's a system accuracy, sum of all the elements, for sum of the diagonal elements divided by sum of all the elements in a confusion matrix. And this is class-wise, true, positive, precision, and recall. And this is also class-wise, precision, recall, and F1 score. We have a direct function in the sklearn to calculate everything, but you should have a fair understanding of what it is.